We'll call the length of curve, and this isn't hard at all. We'll find the length of the curve when the curve is given in parametric equation. So that's what we'll be starting with, that one. Let's start with this. We're going to be finding the length of the curve described by parametric curves. We did length of curve in section 8.1, but do you remember it was like the curve was given as y equals x squared or something? In 8.1, find the length of the curve. Yeah, but it was like this. Right? What if it's in parametric form? How are we going to find the length of the curve if we don't feel like eliminating the parameter? And there's an easy way to do it. Here's the formula, but for the method for doing it. I think we should derive that first, because it's not hard at all. So I'm going to start with section 8.1. Do you recall the formula for finding the length of a curve, or they call it an arc length? It was just the integral of the square root of 1 plus. Yes. You nailed it. Very good. And you go from one x value to another x value, true? Can you help me derive that thing? So the first thing is, I want to get the t's to merge, right? Because I want it parametric in terms of that parameter t. So I'll start with that dy dx, and how about, here we'll make it bigger so we can see it. Let's go into the dy and the dx. Now let's divide them both by d. Because all I'm doing is multiplying a 1 to that. So I'll start there. So let's say I divided the dy by dt and dt, dx by dt. That just means I'm multiplying a 1 expression, right? But now we need this to be in dt, true? So how about this? Let's multiply dt over dt. So far so good? Okay, we're almost there. We're one step away from deriving this. Can you help me put this back into the radical? That dx dt. We're going to just leave that there because we want it in terms of t. How can I put that back into the radical? When I multiply it in there, it'll be a what? A dx dt squared, right? And I'll put it here. I'll make sure I distribute it. So let's just see what happens. I get it into the radical. We'll multiply it inside here. It becomes a dx over dt, but it'll be squared, right? Because it's going back in the radical. Then it gets distributed here, and look what happens. You put it here next to this what? Gigantic dy over dt, dx over dt, squared, and what cancels? And that's just right here. What cancels?
The dx dt.
Dx dt squared. And you're left with the integral dx dt squared plus dy dt squared dt. These will be two t values. So these limits will be in terms of t. I'll call it t1 and t2. So that's an easy way just to derive it from the section 8.1 equation when we found the arc length. It would have worked even if you had 1 plus dx over dy squared dy. Cool?
How come the second dx over dt is squared? Right?
How they cancel?
No, how come that one's squared at the top?
Oh, so this one right here is squared.
That one, the other one.
Oh, and with this being over this is squared too.
No.
Oh, okay.
Right, that one. Yeah, why is it squared?
Oh, why is it squared? And I gather you're asking here too.
Yeah.
This was outside the radical. Look at this. Had no had. We took this and placed it back into the radical. So that means I multiplied, basically, I could have showed another step. I called this the square root of dx over dt squared, is what I refer to this. Because isn't that equivalent to that? And then I had it inside the radical. And then Nicholas, I distributed it. So, okay, multiplied it by the 1. And I distributed it here as well. There it is, sitting there. But then now a lot of these cancel. And that's where this formula merges from. Cool. So this was actually, this formula here is in 10.2. But let's do a problem. Let's find the length of a curve when it's in parametric form. Because in 8.1 we found the length of the curve when it was what? Cartesian. Y equal to x squared. So this is
And 10.2, this is like number 41. This is like number 41 in section 10.2.
All right, oh, and they wrote the word exact, so let me put that down. Find the exact length of the curve. What we have is x equals 1 plus 4t squared. Y equals 4 plus 8/3 t squared. Move this out of the way. Four plus 8/3 t cubed. And he wants you to go from t equals 0 to t equals 2. Oh. Well, that's the formula we use. We're right there. So we're going to do the integral dx dt squared plus dy dt squared. So first thing is we got to get these derivatives, right? But the limits and integration is just going to go from 0 to 2, true? What's the derivative x with respect to t? AT. And what's the derivative of y with respect to t? 8/3 times a 3, then t squared. Is that 8t squared? So far so good. Now let's jam it in the radical. Here we go. 0 to 2. And here comes the length of the curve. Square root 8t squared plus 8t squared squared. Right. What's 8t squared and what's 8t squared squared? Um, 64t squared. This is 64, but now what?
T to the fourth?
T to the fourth. All right. This won't be a trig substitution, but can we simplify that? Can we take something out of the radical? Can we factor?
64 t squared.
I'm going to do that. I'm going to factor. First, I'll leave it in the radical. 64t squared. That's a 1 plus just a t squared. Now I can pull that out of the radical, right? What will that be? Because we're going from 0 to 2. You might say, you got to put the absolute value of t. Well, t's positive, so it's going from 0 to 2. So what do you now get? The integral of 0 to 2. What's the square root of 64? 8. T, but you still have this square root of 1 plus t squared. I don't have to put the bars on there. These are positive, t's greater than 0. Yeah. Awesome. How do you do this one though? It's not a trig substitution. It's not arctan. And it's just a u sub. What makes it look like a u sub? That power is a squared, that's a power of 2, that's a power of 1. So I'm just going to let u equal up 1 plus t squared. What's du? 2d dt. So I want to knock out the t dt. So I get 1/2 du equals t dt, right? Okay. 8. Put the half at the 8. Bye-bye t, bye-bye dt. You just got a hat with a u, dt. U du? Square root of u du. So far so good? And 8 times a half is a what? 4 if you want to make that a 4, but how do you do that integral? U the 3 halves, divide 3 halves, which is multiply 2/3. I still got this 4 here, right? Where's that 4? And did you want to change the limits or just resubstitute?
Change it.
Ah, he likes to change the limits. Interesting, so I'm going to do that. U equals 1 plus t squared. This was a 0. So what's 1 plus 0 squared?
1.
Good. So I mean, this is u equal to 1. He likes to change the limits. What's the upper limit? What's 1 plus 2 squared?
5.
5. You just put it right in there and get your, what is 4 times 2/3? What's that, 8/3? Armando, you got it. Just 5 to the 3 halves. That's irrational. What's 1 to the 3 halves? That's the best way I can write it. Unless you want to write it like Bob. How's Bob write it? Back up book would write 5 square root of 5 minus 1, exact length of curve. Isn't that cool? We just found the exact length of this curve, this parametric curve from 0 to 2. All we had to do was use this formula right here. Any questions on that? I did change the limits though, so if you're a person who doesn't like to change limits, just keep your original 0 to 2 and resubstitute that u to be the what? 1 plus t squared, you get the same answer. Outstanding, that's exactly like the curve. Who's taking Calc 3? Oh, it's like over half the class. Guess what the formula is in 3-dimensional space? The length of curve. So think of some curve in 3-dimensional space like the helix. Guess what the formula is? The formula becomes integral, square root, but you now have how many of these? That's right, there you go. That's exactly what's going to happen. dx dt, dy dt, dz dt. So very good. It's a single integral. Now we'll find the length of the helix. Right, funny looking curve in 3-dimensional space. All right. Well, now we'll get back into the polar coordinates and finding the area of polar coordinates. When we were making, last thing we were doing, we were graphing something that had petals in it. Remember the petals? You can use your calculator for support, right? Sometimes we graphed it in the calculator. Let's do another one with petals, just so everyone's comfortable with that. And feel free to explore this with your calculator too if you'd like. I'll do it without it. Look at it. And I want to see, most important, is can you form that one loop of the petals? So this graph, not all of them have petals. See, some in polar coordinates just form circles. I mean, my gosh, and on that right there, if you graph that equation, that's a very simple equation, or simple curve. That's r equal to 2, meaning the radius of the circle will be 2, will be centered at the origin. Right? That's why polar is so awesome. Equations like r equals 2, or that's a lot more simple than something like this, right? Polar's pretty daggone cool when you're dealing with circles. And so that's what it's there for, but we saw stuff with some petals, and I wanted to start with one of those again. So this is a 10.3. And then after this, we'll talk about what's the formula for finding area of a curve in polar coordinates. And we'll find areas of a couple of curves. So here's this equation now in 10.3. How about r equals 4 cosine 2 theta? And we'll sketch this. Of course, you could use technology to support you here. The one thing I'm most concerned with, can you help me just sketch one loop? Just one loop. So to sketch this, we'll sketch one loop of this thing. It's a bunch of petals. You know, of the polar curve. So everyone, I will make a table and put some values down here. But before I do, can we look at the relationship of this graph in Cartesian coordinates? Now, what's the relationship between r and what? 4 cosine 2 theta in the Cartesian coordinates. What would it look like? That's basically saying if I made that a y, I make that an x. What would it look like? Okay, having 2 theta. What's 2 pi divided 2? That gives me 1 cycle. If anybody's curious how I can figure out 1 cycle is, 2 pi divided by that number is what? So that means it's going to have a cycle of pi. If anybody's curious how I got that. 2 pi divided by 2 means 1 cycle, 1 period will be pi. What's the amplitude?
4.
Gets up to 4 and it gets down to what?
Negative.
Negative 4. So this graph will go here and then come down here. Come back up here and right there. Well, that's the relationship in Cartesian coordinates. If I basically said that was a y and that's an x, this is what it would look like. We're going to craft the polar curve. We're going to get petals out of this. But let me label these. What was this? Pi over 4. Does anyone know how I know that's pi over 4? Wouldn't that be just 1/4 of this? Cool. Pi over 2. This is 3/4. Hey, sometimes students just need a little review of this. So like, why did I choose, how did I know pi was the actual distance here for the 1 period or 1 cycle? The math formula for sine and cosine curves, it's 2 pi divided by that value right there. 2 pi divided by that value will give me the 1 period, or the 1 cycle. That's for sine and cosine. It's different for tangent. Tangent doesn't have a cycle, right? I mean, it has a cycle, but it has a different period. It's not 2 pi. All right, so I'm going to put these over here. What numbers can I use? Well, we got 0, what else? Pi over 4, what's another one?
Pi over 2.
Pi over 2,
3 pi over
3 pi over 4,
4. 1 pi.
and pi, and I just want to make 1 cycle. So what are the values that it takes up? What's going on at 0? What's going on at 0? I'm leaving a little room here. I want a little gap because I might explore, if you're curious, we may explore like putting like a negative pi over 4 here. I mean, you might want to do it. Because the cosine curve, the nature of the cosine curve, isn't it an even function? Right? And so, I mean, what would have happened right here if I extended this? It would have came down to what? Negative pi over 4? And if you recall in the last lesson, this should form 1 loop right in there. This could also do another loop. This would form 1 loop, this would form another loop. But that's why I left a little room here. Feel free to do the same thing in notes and go, all right, I'm going to see what's going on at negative pi. And a negative pi over 4, what would it take on up? It would just be what? 0. What's 4 times the cosine of 0? 4, I mean, you can read it from the graph if you want. What's 4 times the cosine of, that'd be 2 times pi over 4, pi over 2? 0. Does everyone see this? There's that 1 loop. That's what's most important to us today. Because we're going to have to find the area of 1 loop of one of these things. And we'll use this formula here, we'll derive that. But we're going to have to know the limits of integration. That's the biggest challenge. You know how to do integrals. Single integrals, you know how to do those. The biggest challenge will be what are going to be my limits to form that 1 loop. Well, you might pull out the calculator and use the arrows to see what it is, but this right here would form 1 loop. Let's see it. You want to see that sketch? What would it look like? At 0, everyone, theta was 0, how far from the pole was it? 4? But at negative pi over 4, what was it? Where is negative pi over 4? That's swinging down here, right? So you can imagine it was here, but if I swung it down to this angle right here, this thing would just swing and go back to a number what? 0. What's going on when it gets to, that's at 45 degrees. I want to point that out. How did I know, you were asking me yesterday about this, how do I know what's going on between here and that point? I mean, these little points right in here might help me see it. Like these were the values taken on. And that's why it is helpful if you want to explore this with the calculator. Now what happened when it got past 0 and being a distance of 4 from the pole? What happened at the angle of 45 degrees? it came back to a what? A 0. So I'm gonna put an arrow here. This is what happened if I took this curve from here to here. Does anyone see the one loop that gets formed? It gets weird though, because people are like, how'd you go from 0 to 4 to 0? And I know it did this. You might want to look at some other points that were involved in there. And so what I'm saying is like, at this number right here, between negative pi over 4 and 0, I knew it was going to be a positive value, right? So just go, I mean, can anybody invent an angle between negative pi over 4 and 0? What, negative pi over 8? Will that work? Well, negative pi over 8 would be like right there. And that's what we're saying. It'd be a negative angle, but it'd be a certain distance away. That makes sense? But eventually it got to the what? 0, which means 0 from the pole, and it was at a distance of 4. And when you do this on your graphing calculators, TI-83 or TI-84, you just change the mode to polar. And what's a good zoom?
Trig.
Zoom trig. Zoom trig does a pretty good job of zooming in on what you have there. If you want to use the arrows, you can watch it form, like each loop. But this only didn't have just one loop. Has anybody tried this yet? How many loops does that have? 4. Is that 4 loops? This thing will have 4 loops to it, eventually. You go, but it's not, if you haven't even tried it yet, real easy to put into the graphic calculator. Does anyone go there? And we'll come back to this problem later. Just remember, it's interesting. What formed the one loop? From negative pi over 4 to pi over 4. Or what could have been another limit? What else could be limits of integration we'll do later to form one loop? Look at this. Does this help? Another loop should go from what? Pi over 4 to 3 pi over 4. Do you see that? Here, I'll shade it. It's like shading these. They almost look like semicircles, but they're not. Right in there would form another loop. Because what's happening? You're getting that 0 and it's returning to what? It's at the pole and then it's back at the pole. Do you follow me? I mean, if you want me, you can put that in your notes that this is what's going on. Oh, it's at the pole. Then it's back at the what? It's back at the pole. And then it's back at the pole. This thing, it's forming a pedal, goes out and comes back in. It goes out and comes back in. Cool. But this thing eventually has 4 loops. Alright. Hey, great job with that. That's what's most important to me. It's not that, hey, am I gonna have to predict how many loops this has without the technology? No. But what you'll have to do is, in a second, we're going to find the area of the curve, but they'll actually find the area of one loop. Cool. Awesome. Hey, can I race? Excellent, Kate.
Will you do the second loop, please?
Oh, I'll be glad to. So we're going to now form the second loop. And we'll use this as a guide to help us out if we have to. So let's start here. What happens when I plug a pi over 2 in there? 2 times pi over 2 is pi. Cosine of pi is -1. What's 4 times -1?
-4.
And we can see that, like even coming over here, what was going on pi over 2 is at -1. Now do you notice this graph, this relation, Cartesian, we know these R values should be negative down here, between here and here. There's something funny when we plot points in polar coordinates when R is negative. So it went from here back to here. Now where's it going? Well, where's pi over 2? Swing there first. Where's 90 degrees? Oh, I guess I'll swing the curve up here then. Hold up. -4. So what would happen?
It has to flip.
And that's what happened. So it swings it down here. And it moved from here to here. There's a bunch of points between pi over 4 and pi over 2. They're right here. They're all these little points. You and I can plot them, but we can see them. And that's what it would do, would just keep taking on those values until it finally got to the what? Right here. And this would be a distance of 4 away from the pole. That's where this is at. This is actually at the point 0, -4. Now we'll do this. Now, how about to get back to this pi? Or this 3 pi over 4, excuse me. 3 pi over 4, this just turns into what? Is it back at 0? You can use that as a guide. Is it back at 0? So now, where's this curve going? It's coming back to there. It can be a little weird because I'm not plotting, you're going, don't you have to plot more points to see that? Not necessarily if you can use that as a guide. If you can use that as a guide to see, oh, that's what's happening. I would have had all those points in here reflecting all those points that were like right there. Or back up here. Hey, so when they ask you today, they find the area of one loop, Kate, you could set your limits as -pi over 4 to pi over 4, or you could do what? What else would make one loop? From pi over 4 to 3 × 4. Because all these loops have the same area. Does that make sense? Oh, cool. Taking our raise. And eventually it makes 4 loops. One here, where are the other 2? Can you predict? Like there and there, right. And you change this to a 3, it gets a little different. The funny thing is, you change this to a 1, it turns into just a full circle. So polar coordinates, yeah, you change numbers like that, there's coefficients. Be a little different. Okay. Hey, we'll come back to this. But I think I'll leave that. Relationship of 4. Well, that wasn't hard to draw. I can draw that back again. What I need to do now, and let's derive this formula, area of polar coordinates. To do that, does anybody recall in a geometry, probably in a pre-calc course, the area of a sector of a circle? We need that. So what's the area of the sector of a circle? You know, here's a circle. And when this is a circle, a sector is just going from the center outward, like a slice of pizza. That's what it looks like. That's a sector. So how can you get this area right here? The formula, don't worry if you didn't know it, is 1/2 r squared times theta. As long as theta is in radians. Okay? That's the actual formula finding the area of a sector of a circle. So if you're thinking, wait, what about pi r squared, then divide by like a fraction of 360 degrees? If that's what you're thinking, yeah, true, but this is in radians. Cool. Well, then this will help us find the area of the sector of a circle. Sure, in a geometry class, but this allows us to find the area in polar coordinates. Because we're thinking, okay, I don't know. And when you had a graph that, let's say, it does something like this, we could break this into sectors, right? But really, 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 really small sectors. Let me do it again, like this. Cool? And we could send a limit to infinity of all those areas of the sectors. You follow me? So I mean, if this was theta here, you want to just call it d theta? Like a small angle, we can call that what? D theta in there? Just a little d theta. And we want to get this. You go, okay, what I can do is take the area of that sector. What's the area of that sector right there? 1/2, let's say it's in terms of r, some equation in terms of r. 1/2 radius squared times, what's my angle now? D theta? Okay. And we're just going to sum this. And actually, I'll even put it in this notation first. Let's just call it a very, very infinitesimal change. So I'll use change in theta. And I'll call this change in theta like that. And we'll take this, and we'll sum this from towards infinity. I'm going to put I equals 1 and send this to n, and I'll just put like, and we can do like an r sub I here. Like some r sub I, like there's going to be a bunch of these. And we'll turn this into just an integral. What does this turn into? The summation of all these, which will be 1/2 r squared, where r is the equation, d theta. There you go. That r will represent the curve. But if they ask you to find the area of one loop, we're going to have to do the limits of integration, right? These will be in terms of theta. Hey, the book, you'll notice they also write it like this. If you like it. Like a function of theta. Do you prefer that? I'm going to leave it as r because the majority of the problems you see in this section is written as, you know, like y equals x. This is r in terms of theta. So I'll just keep an r there. Sound good? All right. Hey, let's start with one. And I want you to find the area of one loop of a circle. All right. This is in 10.4. Find the area of one loop. funny. When this is in polar coordinates, right? 1/2 integral r squared d theta. You got it. I will do a one loop problem, but I just want to point out, this is number 2. Just from the textbook. This is all they wrote. They didn't make a sketch, they didn't ask you to make a sketch, they wrote r equals cosine of theta. That's all they wrote. And they said, I would go from 0 to pi over 6, they're giving you the limits of integration, they want you to get the area. Inside of here. Inside the area. They go find the area of the region that's bounded by the 0 to pi over 6 of r equals cosine theta. How would you set that up? You don't have to solve it, I'll just, you set this up. What would give you the area? So the wording again, find the area of the region that is bounded by this. What's the area of the region? Bounded by this curve. It means between 0 and pi over 6. And we haven't even looked at this curve yet, have we? What would be to set up this interval?
Would it be 1/2 times the integral from 0 to pi over 6 sine of cosine squared theta?
You got it. Kate, thanks. Outstanding. So this problem, piece of cake. If every problem was like this in this section, they'd all be a piece of cake. Because they gave us the what? The limits of integration, true? So we're like, after we do this, if you want to work it out, we can. After we do this problem, let's look at the hard problem. It's like, well, they don't give us the limits of integration on the one loop. You and I are going to have to figure out what forms that one loop. If you have to use your calculator, just kind of help you support it. Something's going to come up common in this section because of the nature of this formula. How do you do integrals of cosine squareds? Don't we need a trig identity? Don't we need a trig identity to do this? What's the trig identity? We can leave it up here all class. What's cosine squared of like, I'll just put t. What's cosine squared of t equal to? 1/2 plus 1/2 cosine of, yeah, 2t. You can use x. What's the sine squared? It looks just like, this is the one I messed up that one time. I was on the board for like a half hour. I apologize still mad about that. 1/2. Then this is a minus. This doesn't change the sign. It says what? There you go. Those are the power reducing identities. Well, we need them to do those integrals. And they're gonna merge because of the nature of this formula. See the r squared? You're gonna get cosine squareds and sine squareds. If anybody wants to know where these are derived from, if you didn't do that in a trig class or a pre-calc class, they come from those sum and difference formulas. Do you remember that? So if you want to derive that, to help you remember that, that's how you do those. But we need them to do the integrals. So on that note, how would I do this integral? I already got the half out here, but what can I put? Half. You can put another half with it, right? And what's this turn into? You know what? Before I put that half there, I should just write down that identity. What is it? I'll just repeat it. It's what? 1/2 plus 1/2 cosine of, now it's in theta, so I'll write 2 theta. You agree? But how would you do this integral? Any suggestions?
Take out the 1/2.
That's a good idea. Take out the half, back out a half. Well, what's a half times a half? 4. Alright. Bad idea, I like it. Now one of these involves a u sub. That doesn't. What's the integral of 1? That's just theta, right? Alright, everyone, this guy here involves a u sub. Right? Do it equal 2 theta. The integral of cosine becomes a sine, right? So in here you get theta plus 1/2 sine of 2 theta. Get that out of the way, put a parentheses here. That 1/4 is still out in front. Was everyone okay with that? That's via u sub. You can explore it. Let u equal 2 theta. You get that 1/2 to pop up to the sine of u becoming this. And what's the limits? 0 to pi over 6. So what would be the answer to this problem? Just doing this integral here. 1/4 theta, 0 to the power of 6. I get 1/4 of pi over 6 plus, what's 2 times pi over 6?
Pi over 3.
Pi over 3. What's the sine of pi over 3?
Root 3 over 2.
Square root of 3 over 2. So when I have 1/2 times sine of this would be pi over 3, and I get square root of 3 over 2. Now I gotta plug in the what? The zeros. Well, good news when you plug in zeros. And what's a 0 here? And what's the sine of 0?
0.
I like that. So what does this all turn into? Well, I still gotta distribute that 1/4 of that. Unless you wanna leave it like that. We can write it a little better than that, right, Owen? What's the answer to this problem? 1/4 times a pi over 6 plus square root of 3 over 4. I mean, that's fine. Unless you want to distribute the 1/4. What's that distributed?
Pi over 24 plus root 3 over 16.
Good job. Pi over 24 plus root 3 over 16. I haven't looked at Bob, how Bob wrote that. That would be equal to that. Somebody okay with that? Nice. Good deal. This is polar coordinates. Some of the images in the book, they showed you the graph, so all you have to do is look at the graph to determine the limits of integration. But let's get to the heart of the matter. What's the challenging problems? When we don't know the limits, and you and I gotta somehow do that one loop. There you go, let's do one of those. Like, that's the only thing we're concerned with, that one. You know how to deal with these integrals. Just use that nice power reducing identity. We're looking at, what about, I gotta find the area. I'm going to a problem when this is like number 17. Find the area, or 19. Find the area of, or they said enclosed by. Find the area of the region enclosed by one loop of the curve. I want to use the exact words. Find the area enclosed by one loop of the curve. Alright. Find the area enclosed by one loop of the curve. Which one is this like? This is like number 17 from the book. And 10.4. 19. Even number 8. But number 8 had an image. I don't want to do 8 because number 8 is too easy. They showed the graph already. Yeah, they showed it for us. We know the challenge is when we got to make the graphs. All right. So the one I have here, Owen, can you find the exact? Do they say exact? Yeah. It's got to be the exact. And we'll find it for. Let's see. Here. R equals sine of 3 theta. We gotta find the area enclosed by one loop of the curve R equals sine of 3 theta. Number 19 had sine of 4 theta. This problem's a piece of cake. 1/2 out here. What's getting squared? See what I mean? Isn't that area? What's the tough part though? You bet. Look, you know the formula, right? It comes from area of a sector. Piece of cake. I put the R in area squared. I put a half out here. This will give me the area. What's this? Right? How far? What are those limits that form that one loop? So what I have to do is use the tools, the methods we did back in 10.3. So can you help me sketch this, baby? I'll just make a what? Little table. We use theta and R. And look at this, the polar curve. What forms one loop? if it helps, I'm gonna look at this again in Cartesian coordinates. That's why I go way over here. The only reason I keep crossing way over here across the other side of the board, I didn't want you to think this is the polar curve. I'm just exploring that relationship in Cartesian coordinates. It helps me see the one loop. So in Cartesian coordinates, what would this look like? This relationship. That's what I call it. I call it the relationship. What is this relationship in Cartesian coordinates? And after a while, you see a pattern of these. That's the best part. R equals sine of 3 theta. Now, we were just talking about this. What's the 1 period?
2 pi.
2 pi over what? So I'm going to make 4 tick marks. Tick, tock, and put a 2 pi over 3. Now, what's the sine curve do? The cosine started up here in the air and ended in the air. What's the sine curve do?
Starts at 0.
Starts at the origin, swings around, hits the origin again. I'm not the origin, but the x-axis. Then it comes back down and hits here, right? That's the sine curve. How high does this thing get?
1.
Gets up to 1 and gets down to
-1.
-1. And we're saying this is r, this is theta. This is that relationship in Cartesian. This isn't the polar curve. But this will help us determine a one loop. How many know what one loop will be? From there to there. I guarantee it, because there's what's happening at the pole, and this is what's going to happen at the pole. You know? This is given away to me. The only thing is I got to figure out that tick mark.
Pi over 3.
Excellent. Half of 2 pi over 3 is? Everyone, I know the limits now. Just from this. I didn't even sketch the one loop, I didn't sketch the one polar curve. It's because this is taken on a 0, that's at the pole, and there's another 0 of r, right? At the pole. That's when r keeps hitting 0. That would make the one loop. So I know this is going to be from what? 0 to pi over 3. It will be. But let's do this anyways. It's just cool to look at this. 0, what was between 0 and pi over 3? Ooh, thank you. I'll put that here. 0 pi over 6, and then pi over 3. It was 0, this was 0. What was going on at pi over 6? Pi over 6, I'll label it right here when that's pi over 6. It got up to a 1. Cool. Down there, your one loop. One loop. Can you help me sketch it though? Okay, I know we were talking about it before, but if we didn't want to pull out the calculator, how would this graph do? Start at the 0, 0. And then let's move to an angle pi over 6. What's pi over 6 in degrees? So go out 30 degrees, everyone, but how far you got to swing away from the pole? Swing a distance of 1, so here's about 30 degrees. Pi over 6. Swing about a distance of 1 away from the pole, and then what happens?
And then it comes back.
Swing back. Just like 0, 0. 0, 0. And here's the one loop. One loop. 0 to pi over 3.
But we still need
You still got to work the problem. I don't know what you think. I think that's the hardest part of the problem. I think we'll be fine. We're going to use the what? Which one of these? We'll use that one, right? Cool. Hey, can we talk about like shortcuts and patterns? Have you noticed something? What's that number right there? Odd. Well, not only is it odd, it's a 3. And what's that number right there? A 3. Isn't that interesting? Guess what would have happened if that was a 2? Guess what would be, that'd be pi over 2. I'm serious. Now, I'm not going to go down to sine of theta because that's a circle. That's a totally different story, but I'm going to keep going. What if that was sine of 4 theta? Pi over 4. I'm serious. If you can find this helpful, especially in a test, if we're doing sine of pi theta. What do you think this would be? Pi over 5. You could play around with it. Do it all day. You would notice the same pattern. Okay, now be curious. Does that work with cosines too? Actually, it does. Actually, it does. Because cosines like sine. What is its period? 2 pi, right? You'll notice the same difference, okay? But I have to be careful. Does that work for all integers? Hold up, because you get down to like a sine of 1 theta. Now that graph doesn't have all those petals anymore. It turns into just a circle, okay? And when we did the hard part, at least in my eye, we did the hard part. You ready to do the trig identity? Is everyone okay with that? Nice. There's your one loop. Only that one loop right there. One loop. The one whoop, and back here. That formed that one loop. 0 to pi over 3. We need the trig identity. What is it? Well, I'm gonna write it out carefully first. It's 1/2, right? Is it plus or minus? Minus, thank you. Minus another 1/2. Don't be like the professor. Sine or cosine? It's cosine, it's cosine. Now, this is new. I used to put 2t or 2 theta. What's this at? This has a 3 theta in there. Guess what I'll put here? I hope this isn't too confusing to you. Look what I just wrote. I hope you don't find this too confusing. I just wrote 6 theta. And you go, why? Because what do I have to do? 2 times whatever t was. What was in there? What was that t? A 3 theta. Does everyone follow that? Just so you're comfortable with this. What if that was 4 theta? You would have put what there? 8 theta. You got it. And what if that said 5 theta? What would you put here? 10 theta. You got it. Let me put my d theta down. I don't think you're going to have any trouble with this. But we will find, well, let's find the exact area. You know, so if we put this into our TI-84 or TI-83, it's going to put it in decimal form. Let's get the exact area. Suggestions. Do you want to factor out the half? It's up to you. Okay, I will do. Let's factor out the half. Okay. 1 minus cosine of 6 theta. We do know we expect the u sub right there. That'll be a u sub. That's an easy interval. What's integral 1?
Just theta.
Just theta. 1/4. I'll put my brackets so I don't forget to distribute. Here comes the u sub. But we've seen this over and over and over again. We don't have to write out the u sub now.
1/6.
This becomes a negative sine of 6 theta. And what do you divide by?
1/6.
1/6. That's via a u sub. That is by the u sub method. We've seen it over and over and over again. That's what happens. Cool. And what we got plugged in here? 0 and.
Pi over 3.
And good news, everyone. Don't forget, sine of 0 is 0. And when you plug in a 0, you get 0. So this is going to be easy to deal with. The hard part's over. If you think plugging that in is going to be tough, it isn't. Expect a bunch of zeros. Except for this. When you put a power of 3, that stays what? So the answer's not going to be 0. We can see there's some area here. Get the area of one loop. We can tell there's some area. You ready to do it? What's pi over 3 plugged in here? So I'll just plot an arrow and go like this. Look at the answer. 1/4 bracket 0 minus, what's sine of 2 pi? 0. Minus, now plug in the zeros. 0 minus 0. Right? But right here, that very first one had to be the what? The pi over 3. I didn't want you to think the answer is going to be 0. When I plug a pi over 3 into that theta, it just stays what? Pi over 3. So I get 1/4 of pi over 3, subtract, you plug a pi over 3 in here, you get 1/6 of 0. Then you plug in the zeros, you get 0, 0. So what's this final answer?
Times 1/4.
What's 1/4 of pi over 3? Pi over 12. Ooh. What do y'all think? Awesome, Dave.
If you were asked to say find the area of 2 loops or 3 loops, you just take the answer and multiply by
You got it. They don't ask that, but I love it. If they ask, get 3 loops, you're like 3 times that. Because they are all symmetrical. All those loops, you can look at with it looks better with the technology. But they'll all be symmetrical if they ask that. Me on a test, I just asked for 1 loop. Hey, we're gonna do another one of these. Can we talk about patterns again now? Sine of 3 theta. What did this end up being? Pi over 3. Now look at this answer. This was pi over what? 12, which is 3 times what is 12?
4.
Okay. Do you notice that? We want to see if that always happens too? Where you say this final answer will just be what? 1/4 of pi over a 3rd. You want to check that out? Let's do it. Let's do another one. Let's do one cosine. You ready? How about cosine 2 theta? Didn't we have that up there earlier? Something like that. I don't think I had a 4 in front. We'll just leave a 1. All right, let's do a 1. And let's see if that happens. Sound cool? This one will go quick. What's that in Cartesian? See, now you're getting faster. What is cosine 2 theta in Cartesian? In case, I just want to find the limits of integration. Tick tock, tick tock. What's 2 pi divided 2? Pi. So this is what? Pi over 2. This would be negative pi over what? 4? Pi over 4. Starts here, gets down here, comes up here. We know about the cosine curve. Whoop, 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 whoop. This graph goes back down here if you want to know. Anybody know what we can do for limits of integration? Give me some options. What would form one loop? That would work. And when she hasn't even done this, she already knows what would form one loop. I want you to see this. You can go from negative pi over 4 to pi over 4. That should form one loop. How does Kate know that? Because she noticed it's going to hit the pole here and it's going to hit the pole there again. This is why I want you to concentrate on. When we do our polar graph, it's going to be at the pole there, it's going to be at the pole there. What else could I have done? I could do pi over 4 to, what's that? Pi over 4, but I'll use yours. All right, negative pi over 4 to pi over 4. I'll put the half in front. And what do I gotta, oh, find my error. I'm worried this happens on a test. I've seen this before. What's messed up? And I'll give you a question, but what did I screw up? Don't forget to square that, right? Very good, I'll put it here. Okay, Connor.
So like on a test, can we just show you that?
Heck yeah.
Instead of doing like all.
Heck yeah.
Okay.
I think that's great. Or you might even say, hey, I knew this in my head. I knew mentally that these would be the limits.
Okay.
You know, I love it. Now I'll go in here and write it, but we're like, what would have happened for that one loop? Bless you. This is what would have happened, then at 0 got to a what, a 1? I think it's awesome.
Thank you.
Hey, but didn't we have a shortcut that could have worked? So I'm gonna write this. Kate, you were right, this is perfect, it's gonna work great. It's gonna work great, but didn't we have a shortcut we were talking about? Where I said, no matter what, sine or cosine, I could do what? 0, 2, what's pi over that number?
2.
So I wanna make sure everyone sees this. I also could have started the problem like this. Look what I did.
It's the same distance, isn't it?
Because it's the same distance. So I wanted to point out that pattern I was talking about still works with the cosine. As long as this number is higher than a 1. When it forms all the petals, look. Higher than the 2, see it? That's exactly giving you the same answer. And plus, students like this sometimes because you put a negative pi over 4 that messes up your final answer. True? Get a 0 in there, it's a lot easier to work with.
So we have a variety of different limits that we can use.
A variety, a total variety. Look on this graph where it went from. If it went from 0 to pi over 2, it was funny. It went from here to that area and that area. But do you agree these two areas add up to that? You see the symmetry, very good. And that's what's happening here. Same thing with that polar graph, which would have done what? It would have went here and then back like that. And when there's that, there's this one loop we're talking about. For this one, but you could have done this. Cool. Okay, let's do all the math. I bet you can predict the answer. What's 1/4 of pi over 2? What's 1/4 of pi over 2? Pi over, let's see what we get. Okay, let's play it out. What's the trig identity? 1/2, take it slow. 1/2 is a plus or minus. Plus 1/2 is sine or cosine? Cosine, and what do I do with that 2 theta? Because I got to multiply that 2 to it. You get 4 theta. My limits are 0 to pi over 2. Now, what are your suggestions? Back up to 1/2? 1/4. 0 to pi over 4. We're rolling. 1 plus cosine 4 theta d theta. All right. What's that interval? I get 1/4. I'll put a big bracket. Theta plus, what's this become? Sine of 4 theta over a 4. Oh, go ahead. Oh, yeah, thank you so much. I'm going to keep that pi over 2. Thank you so much. I'm going to keep the pi over 2 like we had before. I thought this would be easier to work than that. But Kate, this would have worked. But he's right, I got to make sure I keep it 0 to pi over 2. 0 to pi over 2. 0 to pi over 2. Unless, here's something else, I don't want to confuse anybody. If I went 0 to pi over 4, I could do that, but I'd have to eliminate the half. Does that make sense? And because of the symmetry, couldn't I do that? If I just put half that limit, 0 to pi over 4, and just remove the what? The half, because of the symmetry, right? Same thing's happening with those loops. But I'll leave it, Hey, what do you get out of this? What do you get out of that? 1/4 pi over 2 plus, put a 0 in there, what's the sign of 0? 0 minus, now put your zeros in there. So what's that answer? Just like we thought, pi over what? Hey, Connor, that's the only thing I don't want someone to do on the tests. They get the problem, they just look, they just go, pi root. 1/4 of that, I know. Just show some work, you know what's coming up though, right? I like when you all see patterns. I don't like those being like hidden from you. You can really see that. This just keeps happening with this. Hey, one more of these. So we do like, I'm gonna pick one near the end where two graphs meet each other, and then you and I gotta figure out where the two polar curves meet each other. I'm gonna draw them for you. When can you find the area enclosed by, now this is how the author wrote this. Last problem. Can you find the exact area of the region that lies inside the first curve and outside the second curve? Here's the first curve. R equal to 2 cosine theta. Oh, by the way, I'm taking number 23. This is in section 10.4. That's the first curve, and this is the second curve. R equals 1. Okay. So I'll get this out of the way. We won't need that.